Alright, so as I just mentioned, I would like today to take a step forward with respect to what we said we worked on so far, because I would like to start to talk about the response to harmonic excitation. So far we talked about free systems, which means that we have spring mass, sometimes damper if we have a damped system. And in that case, again, so far we talked about free system, which means that there were no external forces applied on our mass, for example. We were relying basically on initial conditions in order to have motion. If we have a free system, meaning without external force, where the initial conditions, position and velocity, are zero, there is no motion and is a static system. Now we are going to start to work again on systems that are forced, and we will need to understand what happens when we apply an external force to this type of systems. Now, from a mathematical point of view, things are getting a little bit more complex, and this is because we are still dealing with differential equations. We are still going to deal with ordinary differential equations, linear differential equations. However, we are going to deal from now on with non-homogeneous differential equations. And this is what will make the big difference. Before we were working with homogeneous differential equations, and now we are going to work with non-homogeneous differential equations. However, I would say that things are going to get a little bit more interesting, because especially from a physical point of view, because now we are going to see what happened, and especially we are going to have a better understanding of the concept of natural frequency. In most of the problems that we saw so far, we were searching for the natural frequency, and that was it at that point. Now that we are going to work with forced systems, we will have a better understanding of why we need to determine the natural frequency of a certain system. Make sense? Alright, so again, we will go through a little bit of derivation today to see what happens when we have a forced system. So when we have a forced system, it means that we apply a certain force on our spring mass system that changes in time. When the force changes in time, it can change in many different ways. It can change in a random way, it can change with a step, for example, or it can change with a sine wave or a cosine function, which is like the most simple case that we can see. So this is where we will start from. So when we have an external force, again, that has like a cosine or sine function, we can write as F. So force as a function of time can be in the form F0 multiplied by, let's say, cosine of omega t, or for example can be f of t equal to F0 sine of omega t. Which means that when we look at the external force that we apply to our system, we still need to look at two main parameters. One would be the amplitude of this force, which we can indicate with F0, and the other parameter is the frequency of the force that we, or the frequency of this time-dependent force. So again, these two parameters are what we will focus on when we analyze the system. Again, it can be with a cosine function, it can be with a sine function, not a big difference from a physical point of view, slightly different from a mathematical point of view, because the actual function would look a little bit different, but it's just a matter of shifting the function along the horizontal axis. So we can start by looking at an example where we have like a cosine function. So let's assume we have a system that looks like this, where we have our mass that is connected to the wall with a spring. Of course, we have the mass m, we have the elastic constant of the spring that we can indicate with k, and then, as we said, we are applying an external force. So we can apply the force in the same direction of the degree of freedom. In this case, the mass moves in the horizontal direction, so the force is applied in the horizontal direction. And we can again consider the example where the force is F0 cosine of omega t. Okay, so I want you to spend 2, 3, 4 minutes on looking at this system and drawing the free body diagram and trying to write the equation of motion of the system. Alright, in this case, the free body diagram should be pretty intuitive, because if we look at the body, we have, of course, the weight in the vertical direction downward, the normal force from the ground also in the vertical direction upward, but we are not interested in these two because there is no motion in the vertical direction. The motion occurs only in the horizontal direction. So we look at the forces in the horizontal direction. In this configuration that we have here, where the force, the external force is pointing towards right, this is what we have. So this is our F of t, and then the force from the spring would be in the opposite direction. We can call this Fs. Okay, consider that this force here is a force that changes in time. So what we are doing here, we are actually taking like a picture of an instant of what's going on the system. So let's assume that the maximum value that the force can get is basically F0, because the cosine function can go between +1 and -1. So the maximum that we can get is F0. The minimum that we can get would be negative F0, because this can be -1. So again, this is just again a picture of an instant, but we may have situation which we may have again instance in which this force, instead of pointing in the right direction, points in the left direction. So when the force points in the right direction, it means that this is pulling in the right direction, which means that the spring is stretched. If the spring is stretched, it means that it has the tendency to pull the body back. So it means that the force of the spring must go in the other direction. Make sense? If we were in a different situation where in an instant the force, the external force was pointing in the left direction, in that case we were simply squeezing the spring. If we squeeze the spring, it means that the spring wants to push back the mass, and also the force of the spring would point in the opposite direction. So basically, no matter which instant we are looking at, the two forces must be opposite to each other. Which means that mathematically doesn't change anything if we have the external force toward right and the spring towards left, or if we switch both with the external force towards left and the force of the spring towards right. And this is because we look at the summation of forces in the x direction must be equal to m x double dot. So the summation of forces, we have f of t minus kx. Remember that the force of the spring depends on the elastic constant and on the displacement of the spring, the displacement of the mass. So we have f of t minus kx equal, so this is the summation of forces, equal to m x double dot. the acceleration in the x direction. Of course, also this one and this one are function of time. Just to simplify, we write x and x double dot. We can rearrange this expression, and what we obtain is mx double dot plus kx equal to f of t. This is the equation of motion of a forced mass spring system. Okay? We can rearrange, or actually we can rearrange, so we have x double dot plus k over mx equal to f0 over m times cosine of omega t. And we already know from what we studied before that this term k over m is omega n squared, and we can introduce a new parameter, which is basically the amplitude of the external force normalized with respect to the mass, exactly like we normalize with respect to the mass the elastic constant of the spring. So we can write F0 over, so capital F0 over m as lowercase f0. With these two, our equation becomes x double dot plus omega n squared times x equal to lowercase f0 cosine of omega t. So exactly like we did with the free systems, even in this case we obtained a standard form of the equation of motion. This is lowercase f naught. This would be the amplitude of the external force normalized with respect to the force, which means we divide this uppercase f by the mass, and we obtain this new term here that we indicate with lowercase f. Now, as you can see, if you look at the equation without this term here and we place 0 instead of this term, we have the same that we had when we were looking at free systems. But now we have this extra term, so it means that the equation is not homogeneous anymore. Now it is a non-homogeneous equation, which means that in order to solve, we can still look at what we had before for the homogeneous equation, but that's not going to be enough. We need to look at something more. So in general, when we have a non-homogeneous equation, the general solution can be the solution can be written as a summation of two contributions. So this uppercase x is the total solution, is again the summation of two contributions. The first one is the solution of the homogeneous equation, and then the second contribution will be the solution of the particular equation. Now this one, the solution of the homogeneous equation, we already have that actually. We found before from the homogeneous equation, so we can recall the exact same result that we found when we were looking at the free system. For this one, this is the part that we need to work on, so the particular solution. Now, for an equation like this, the particular solution can be written as follows. So we have xp of t, of course all of them are functions of time, as I'm gonna use this little signs to indicate that this is like uppercase x times cosine of omega t. And now we have to do something very similar to actually what we did before, because what we are going to do is to take this function here, which is again the particular solution. We have to derive the first time and have to derive twice, and then we can plug in the equation of motion, and then from this we will find actually the particular solution. So let's go with the first derivative. Of course, derivative with respect to time. So this is a product. Excuse me. This is a constant. So this remains. The derivative of cosine is negative sine. So I put the negative sign in front. And then we multiply by omega because this is a compound function. When we look at the second derivative, we have to derive this expression here, so we have x double dot. So here we have negative x is still there, the derivative of the sine is the cosine. We still have this other constant omega. We need to multiply this constant omega by the derivative of what we have here, which is another omega, so this becomes omega squared. Yes. This one is the same of this one, yes. Yeah. Sorry, I was trying to simplify a little bit the notation and I used just p instead of part, but yes, this is the same of this. So with these steps, we are searching the particular solution. Sure. Other questions? So now that we have the second derivative and the function, we can plug in the equation that we had before, and then we plug. When we plug, this is what we obtain. We have negative big X omega squared cosine of omega t plus big X cosine of omega t and omega n squared equal to f0, this is the lowercase f0, cosine of omega t. As you can see, this term, cosine of omega t, shows up in all three terms of the equation, so we can get rid of it, and the equation becomes big X omega squared plus big X omega n squared equal to small f0. So this is what we need to find. We need to find the amplitude basically of our particular solution. So from this one we can obtain x big X equal to f0 divided by omega square omega n square minus omega square, which means that the particular solution, what we will find before, is going to be equal to this amplitude that we just found, so f0 divided by omega n square minus omega square multiplied by this term here, cosine of omega t. So this is the particular solution. Yes, yes. we make this assumption that the form of the solution is like this because the forcing form is, the external force has this form here as well. So basically we assume that when this force is applied to the system basically behaves in the same way of the force that we apply from outside, basically. So that's why when we have this force, this external force, we assume that our particular solution will have this form here, which means that the time function would be cosine of omega t, and we just need to figure out how big would be the oscillation. So it means we have to figure out this x, this big X here, which is what we just did. Make sense? And if we look at this expression here of the big, this is again the big X, we have f0 divided by omega n squared and minus omega squared, which means that the amplitude at which the body will oscillate, go back and forth, depends heavily on the applied force, because it depends on this lowercase f0, which depends on the amplitude of the force, and it also depends on this omega square, which is something that we also see in the external force, but it also depends on the system itself, because it depends on this omega n. This omega n, exactly like we did before, is a term that depends only on k and m. So the elastic constant of the spring and the mass of the object. Makes sense? Any other questions so far? Remember, as always, when we look at equations, we need to understand the physics behind the equation. Makes sense? Alright, so now we have this, that is the particular solution, which means that when we go back to what we had before for the total solution, we could plug this term here in this particular solution. We also said that the homogeneous, that this term here is the solution of the homogeneous equation, and we already have the solution of the homogeneous equation. I don't know if you remember, but a few weeks ago we said that the solution of the homogeneous differential equation can be written in different ways that are all equivalent to each other. And I think we did that one on February 5th when we were looking at this table here. We used this form, the a sine of omega n t plus v, but we also said, okay, we can write the same thing, we can write this in another form, which will be this one, or we can write in a third form, which will be this one. Again, all these three are equivalent, and we can go from one to another one using these relations here. Now, from a mathematical point of view, in order to look at the forced system, it's easier to have the solution of the homogeneous equation in this form here. But remember, this is exactly equivalent to what we have here. So now we are going to use this form of the solution of the homogeneous equation. So going back to where we were before, again, if we plug what we just saw in the other page here, and if we plug this here, this is what we obtain. So our x of t will be equal to a1 sine of omega n t plus a2 cosine of omega n t plus this term that we just found here. So it would be f0 omega n squared minus omega squared times cosine of omega t please let's make sure that we don't make confusion between this term here, omega n, and this term here, omega. Omega n is the natural frequency, which means it depends only on the k and m, and this is omega, which is the frequency of the external force, because this is how we defined the external force, F0 cosine of omega t. Okay? What should we do now? Are we done? Can we plot our response? Exactly. We still need to find the amplitude of the entire response, which means we need to find these two terms here, A1 and A2. A1 and A2 are two constants that come from solving basically the differential equation. Once we have these two constants, we have to find them in order to find the total solution. How do we find them? What do we set? We need initial conditions. So since we need to find the two constants, A1 and A2, what we need to set to 0 would be the velocity and the position. So exactly like we did before, that we found the constants. In that case we were searching for A and phi. Now we search for A1 and A2, but still two constants. We need to apply the initial conditions, which means we set the initial position to a certain x0 and the initial velocity to a certain v0. Makes sense? So the position is already here, is given here. So the position when the time is equal to 0 means that we have to plug 0 here, here and here. So this function becomes 0, cosine of 0 is 1, so this is A2. This term here becomes f0 divided by omega n squared minus omega, because this is also 1. And as we said, we plug this, we equate this to x0, our initial position. This is actually one equation with one unknown. Our unknown is A2, so we have that we can rearrange. So we have that A2 is going to be equal to x0 minus f0 divided by omega n squared minus omega squared. Make sense? So as we said, so we found one constant, which is A2. We have to find the other one, so it means we have to apply the next initial condition. In order to find the next initial condition is related to the velocity, so we need to find the velocity first. The velocity will be the derivative of the position, so we have to take this function and we derive this function. Unfortunately, I have to turn the page. Alright, so we have again the derivative x dot so I'm going to write it and then I will go back and forth. So we have A1 cosine of omega n t times omega n, which is the derivative of this first term here. A1 sine of omega n t becomes A1 cosine of omega n t times omega n. Then we have another term, I'm going to write on the other line, which is A2 sine of omega n t times omega n times negative 1. so this would be the derivative of this other term here. So the constant remains, and then derivative of cosine omega nt would be sine of omega nt times omega n with the negative sign. And then we have the third term, which is f0 divided by omega n square minus omega square. This is a constant that multiplies sine of omega t and also negative 1. We need to find the value of this function when t is equal to 0, so the initial instant, so x dot when t is equal to 0. This actually simplifies significantly, because this term is the sine of 0 becomes 0, so we get rid of this. This term also sine of 0 becomes 0, so we can get rid of it. This cosine omega nt becomes 1, so this function, when t is equal to 0, becomes simply a1 omega n. And we said that we equate this one to the initial velocity that we call like v0. This is lowercase v0. Even in this case, one equation, one unknown. Our unknown is a1, so we have that a1 is going to be equal to v0 divided by omega n. These two, so the question is why we didn't pull out omega here. This is let me see, let me go back, because I forgot to write omega, so we need to multiply this one by omega. Thank you very much. Thank you for trusting. Fortunately, even with or without that omega, this would have been the same one. So yes, we need to multiply by omega. Thank you very much for pointing this. So we have our notes correct. So now again, we found the second constant, a1. Here from the previous page we have a2. So we can actually write the full solution where we have a1, a2, and it becomes x of t equal to v0 divided by omega n, which is what we have here, times sine of omega n t plus x0 minus f0 divided by omega n square minus omega square multiplied by cosine of omega nt, and then we have another term here which is plus f0 divided by omega n square minus omega square times cosine of omega t. I know this omega nt is a little bit squeezed because I have the whole of the paper, but this is omega nt. Makes sense? Any question about this? So can now can we plot now this function? Now we can, because assuming that we know basically the properties of the system, which means we need to know k and m, assuming that we know the force that is applied, so the frequency and the amplitude of the external force, and also assuming that we know the initial conditions, all these basically become numbers, and we can plot our response. So this means that every time we have a single degree of freedom undamped forced system, the response will look like this. So in the future, if we have a case like this, we don't need to go through the derivation again. We can just pull up this function, and this will be the response. Of course, we have to make sure that the external force that we apply on the system has this function here. So F0 cosine of omega t. Because even if we have a function that looks like this as external force, our solution will look slightly different. Make sense? Now, yes, this is the x total, which is what we had here. This x total as a summation of as a summation of homogeneous and particular solution, the total, and what we have here is exactly the same thing, is the total solution, summation of homogeneous and particular solution. This is the solution of the non-homogeneous differential equation, yes. Any other question about this? It would be actually good practice to consider a system where we have an external force with this form here, F0 sine of omega t, and find the total response, the total solution of that type of system. I will probably give you this in an homework. Make sense? Alright, I would say now what we can do, we can go through an example. Alright, this is the example that we can look at. So we have a system that is the same that we saw basically in our example here. And now we have numbers because we have K equal to 2000 Newton per meter, so we know the elastic constant of the spring. We also know F0 here, that is like 20 Newton, so it's the amplitude of the external force. We also know the frequency of the external force. This omega here is the frequency of the external force. And then we also have the initial conditions. Both are zero actually, initial position, initial velocity. And we know that the maximum amplitude of the response, so this x max, is equal to 0.1 meters. From all these pieces of information, we should be able to find the mass of the object. So please spend a few minutes on this to try to figure out how to approach it.